Hello everyone. Have you ever tried balancing a scale so that both pans stay perfectly level? Or watched a ladder resting without slipping? These are examples of equilibrium of rigid bodies. In physics, we say a body is in equilibrium when its linear momentum and angular momentum remain constant. That means no acceleration in translation and no acceleration in rotation. The conditions are simple. The vector sum of all forces equals 0 and the vector sum of all torques also equals 0. Written as sigma F equals 0 and sigma tau equals 0. Both must hold together for complete mechanical equilibrium. Now, let's break these vector conditions into scalars. In 3 dimensions, the force condition splits into 3 equations: sum of forces along x, along y, and along z each equals 0. Similarly, the torque condition splits into 3 equations: sum of torques along x, y, and z axis must vanish. So in total, we have 6 independent conditions for equilibrium in 3 dimensions. For simpler coplanar problems, only 3 are needed, 2 for forces and 1 for torque. This makes equilibrium analysis systematic. But can a body satisfy one condition and not the other? Yes. Imagine 2 equal parallel forces pointing the same way. Net torque may cancel, but the net force is not 0. The body translates but doesn't rotate. Now take 2 equal and opposite parallel forces separated by some distance. Net force is 0, but net torque is not. The body rotates without translating. This special case is called a couple. It is simply a pair of equal, opposite, non-collinear forces that produces pure rotation. We encounter couples every day. When you twist a bottle cap open, your thumb and fingers apply equal and opposite forces. The result? The cap rotates without slipping sideways. Or take a compass needle in Earth's magnetic field. The north and south poles feel equal but opposite forces. These cancel out in translation but add up as torques, making the needle rotate until it aligns north-south. The moment of a couple depends only on the distance between the forces and their magnitude, not on the reference point. That's why bottle caps open reliably regardless of where you hold them. Now let's look at levers, one of the oldest machines invented by humans. A lever is simply a rod pivoted at a fulcrum. For translational equilibrium, the upward reaction balances the downward forces. For rotational equilibrium, the clockwise moment equals the anticlockwise moment. That gives us the principle of moments, d1 times Fn equals d2 times F2. This is why a longer effort arm reduces the force you need. Mechanical advantage is the ratio of load to effort, or equivalently, the ratio of effort arm to load arm. That's why crowbars and scissors make heavy work easier. Next, the concept of the center of gravity. We define it as the point where the entire weight of a body can be considered to act. If you imagine gravitational forces acting on each particle, the total torque about this special point vanishes. In uniform gravity, the center of gravity coincides with the center of mass. In practice, we can find it by suspending the body at different points and drawing vertical lines. The point where they intersect is the center of gravity. That's why a plumb line is so useful. Let's solve a couple of examples. First, a uniform bar 70 centimeters long and 4 kilograms in mass is supported at points 10 centimeters from each end. A 6 kilogram load is hung at 30 centimeters. To find the reactions at the supports, we apply 2 conditions: sum of vertical forces equals total weight and sum of moments about one support equals 0. Solving, we find one support carries about 55 newtons and the other about 43 newtons. Second, consider a ladder 3 meters long, mass 20 kilograms, resting against a smooth wall with its base 1 meter from the wall. Forces acting are weight at its midpoint, normal reaction from the wall, vertical reaction and friction at the base. By writing force equations in horizontal and vertical directions and a torque equation about the base, we can solve for all reactions. This shows equilibrium requires both force balance and torque balance working together. So to wrap up, equilibrium of a rigid body is achieved when both net force and net torque are zero. In 3 dimensions, this translates into 6 scalar conditions. Couples show us how pure rotation can exist without translation. The principle of moments explains how levers work, and the center of gravity gives us the effective point of action of weight. These ideas together ensure stability, from ladders and bridges to balancing acts and machines. I hope this session gave you clarity and confidence on rigid body equilibrium. In the next one, we'll explore further into rotational dynamics with exciting applications. See you then.